Just exactly at the moment of euphoria that said, we have this wonderful material, we all rushed out, made it, we passed a current into the wires, and we found that almost no current went before the onset of resistance. So what is it that goes wrong, therefore, when you go to high TC materials? Well, pretty quickly it was possible to see that the obstacle to this current were the grain boundaries, those very grain boundaries which are exactly so beneficial in the case of niobium-3 tin.
Well, the samples produced by chemists are usually polycrystalline materials because this is the standard form for characterizing solids and for making simple measurements. And I suppose there's an implicit belief that if something is a superconductor, then we'll be able to discover this even in a granular solid. Now, that is not always true. There is certainly one very well-established exception to this, which is the strontium-2 ruthenium-04 superconductor, which superconductivity was only discovered when good quality crystals were made and the transport properties were recorded. In fact, I think it's still true to say even now that superconductivity has never been measured in a granular sample of this material, although a great deal of the physics has been elucidated from single crystals.
In order to define intrinsic properties of material, you need single crystals. For example, superconductors are very anisotropic compounds. So it's almost impossible to study the anisotropic properties on powder material which contain millions of crystals of different orientation. That's why we need single crystals.
So this, of course, suggests, well, should we make single crystals of everything? The answer is almost certainly no. But if you do make single crystals, it's certainly worth measuring physical properties, even if they've been allegedly established completely from polycrystalline materials, because if nothing else, you'll get better quality measurements, and you may simply discover some kind of phenomenon that's missed in a polycrystalline sample.
All known crucible material reacts. Aluminum oxide reacts with melt. Barium zirconate, the best material found up to now, reacts with a melt at the temperature of crystal growth. In order to avoid impurity from crucible, you can try to use crucible-free methods like mirror furnace method. So melting zone or traveling zone method using a mirror furnace. This way you can prevent impurity from crucible. The problem is it's not so easy to grow superconducting crystals using this method. So we have to use crucible.
Yes, as a solid-state chemist and as a crystal grower, I know that we have to be very careful about what we make. So when we make a crystal, first thing we want to be sure of is that they are single crystals. We want to make sure that they are homogeneous, because if they are not homogeneous, if you grow a crystal 5–10 centimeters long and you dope it, you put a substituent into it, and if the concentration of this substituent varies along the crystal, the physical properties can change drastically from one end to the other. So what we first do usually when we grow a crystal, we check with X-ray, or mostly with neutron diffraction, we check that they are really monocrystalline. Then we do what we call the rocking curves, which allow us to understand what is the possible mosaicity of the crystal, what is the crystalline perfection. And once we are sure that they are perfect, we check the composition, how, very carefully, how an element is distributed along the crystal. And only then we start discussing with physicists, and we let the crystals go, or we study the crystals with them.